Okay, we're now ready to show mathematically that these functions come out in this order in terms of which one dominates the next. So we're going to show that the exponential dominates n cubed, for example. Okay, so how do we do that? We use something called Littleo notation, but first I want to review Bigo notation again, because the definitions are so similar, but there's a really important difference. So I want to compare them side by side. So Bigo says if, or a function f of n is big O of a function g of n, if it is possible to find a constant c and an associated constant associated to that c, so that f of n is less than or equal to that constant times g of n whenever n is greater than n sub c. So the game we play is that we upper bound f of n by g of n scaled by some constant beyond a certain point. So it is true here that n cubed is big O of n factorial, because even though n cubed is greater than n factorial at the beginning, if we choose a constant of 1, past a certain point, n factorial is going to dominate. But we want to say something a little stronger than that, right? Because, I mean, it really seems like n factorial is growing much faster than n cubed. So n factorial is not a tight upper bound for n cubed. It really dominates. So let's now define Littleo notation. So we say a function, and this isn't in the book. So, but again, the book reviews some stuff from 174, so we're able to go beyond it, and I think this is very important. So we say a function f of n is little o of the function g of n if for all constants c greater than 0. And actually, I didn't specify this, but it's implied that the constant, we understand that the constant that we're choosing needs to be positive. Okay, so function fn is little o of g of n if for all constants c greater than 0, it is possible to find a constant n so that f of n is less than or equal to c g of n whenever n is greater than n sub c. So these are looking really similar, but there's one crucial difference. So this one says we only have to find one constant to make this true. And we saw in class, it doesn't matter how big this constant is, just choose it in a way that's as convenient to you as possible to make the proof simpler. But here, this says something much stronger. We're going to have to work a little harder to prove this. Because it doesn't just say you have to find one constant. It says for all possible constants that you could possibly choose that are positive. This has to work. So my worst enemy can come in. And say, well, I'm going to choose your c to be 10 to the negative 100. So a super, super tiny number. Okay. And I'm going to have to find an m sub c so that beyond that range, even scaled down by this really, really small number, g of n still dominates fn beyond that range. Okay. Now, so we need to introduce slightly fancier machinery for these proofs. I find it's helpful if we rearrange this equation a little bit, or this inequality, to say that, well, let me divide both sides of this inequality by g of n. So what this is really saying is the ratio of f of n to g of n needs to be less than or equal to whatever constant I choose when n is beyond a certain range. So that's really what this says. So let's look at an example. Let's say that f of n is n squared and g of n is n. Oh no, sorry, let me do the other way around. Let me say f of n is n and g of n is n squared. So I want to show that n squared is little o or that. So really, what I'm trying to show, I want to show. Sometimes I get the order mixed up. I want to show that f of n, really that n, f of n equals n is little o of gn, which is n squared. Okay. So yeah, I've kind of said this, but let me really say it again. You know, Bigo notation provides an upper bound. Little o notation says something a little different. It is an upper bound, but it's a stronger upper bound. That really says that f of n is dominated by g of n. Or in other words, that f of n grows strictly more slowly than g of n. Okay. So we've really found something. If we found that f of n is O of g of n, then we've really found that f of n scales better than g of n. It doesn't grow as quickly as g of n. So we like that from an algorithm's perspective. So in this case, we're really going to say if f of n is little o of g of n, then we like fn better than g of n for algorithms. Okay. So again, another way of saying that is that the ratio of f of n to g of n should be less than or equal to whatever constant I choose. So let's look at this example where I say, perhaps, you know, I'll look from 1 to 100, and my f is n, and my g is n squared. And let's say that the constant that I choose is 0.01, so a pretty small constant. Okay, so let me plot f. I'll plot g. No, actually, let me just cut right to the ratio. Let me plot the ratio of f to g. Now I'll plot the constant. And I want to see if it's true that beyond a certain range, this ratio is below or less than or equal to this constant. Okay, so I'm drawing the constant in orange. It's a little hard to see, so let me put this on a log scale. And let me go a little further. Okay, so really, this is kind of intuitive. The ratio of n to n squared is 1 over n. 1 over n is less than 1/100th whenever n is greater than 100. Okay, but my adversary could be a little meaner than that, and they could say make this, you know, make the constant even smaller. But I'll see that it's still possible. See, now if I go past 1,000 now, I can still find that this ratio is bounded by this constant. Okay, I can go even smaller. Now I've got to go up by another order of magnitude, and I can still do it. Okay, so that's the point. Now, if you're, you know, your mind should be thinking and reminiscing back to calculus now, because really this is saying something about a limit. Okay, so there's a little lemma or theorem that we can state that's going to help us prove these relationships. It says that if the limit, so limit as n approaches infinity, of the ratio of f of n to g of n is 0, then fn is little o of g of n. So here's a fact that we can use to help us. Okay, sorry, I'm just trying to get the formatting right here. I've been using LaTeX this whole time, if you ever heard of that. Anyway. Okay, there we go. Now this looks nice. So the limit as n approaches infinity of this ratio, if I can make that 0, if that turns out to be 0, then we say that f of n is little o of g of n. So f of n is totally dominated by g of n. So let's look back at this example that we had, where f of n is n and g of n is n squared. So somehow I have to show that the limit as n approaches infinity of fn over g of n, which actually ends up being, okay, well, I'll write it out. So n over n squared. So we need to evaluate this limit and show that it's 0. Well, here's where we go back and put our calculus or pre-calculus hats on. And we multiply this by a fancy 1. So we're going to multiply both the numerator and the denominator by 1 over n. So 1 over n is 1. So I'm multiplying by a fancy 1 here. That doesn't change anything, but that allows me to rewrite this as the limit as n approaches infinity of 1 over n. Okay, so I'll just distribute this through and I get this. I'm being very rigorous here, okay? I mean, you could probably see that, this limit is the same as this limit. I just, had to take the factor of n out of both the numerator and the denominator. Okay, so now, this is, we're pretty much done the proof at this point because we can see that it's very clear that this limit's going to be 0. I can choose, any number I choose that's arbitrarily close to 0, it's possible for me to find an n so that this is smaller than that. So this is definitely true. So this implies that that n is little o of n squared. Okay. All right, so that's one of the pieces of the puzzle here. So we've shown that now we've rigorously proved that this blue curve really is dominated by the orange curve. Okay, so n squared is worse than n in that sense. But we can go further than this. A more general statement we can make is that if fn is n to the a power and gn is n to the b power, where b is strictly greater than a, then f of n is little o of g of n. So you can prove this using very similar techniques. So in other words, this is kind of crazy. Sometimes people hate notation like this. It kind of obscures the meaning. In English, what this is saying is anytime I have a monomial f of n, which is to a smaller power than another monomial g of n, then f of n is little o of g of n. So you could prove this in a very similar way. So just some examples of this. This implies that, this implies the above, so that n is little o of n squared. It also implies that n squared is little o of n cubed. It also implies that n is little o of n cubed. And I can, anytime I choose, these are all true. So anytime I choose a power of n that's greater than another power of n, I can show that that power of n dominates. Okay. So this is n to the 1, while n squared dominates n to the 1. This is n cubed dominates n squared. Nice. Okay, so we're able to knock out those binomials pretty easily. And actually, the constant works that way too. It works within this framework. This also implies that 1 is little o of n to the anything when a is greater than or equal to 1. Okay, so any n raised to any power greater than or equal to 1 is going to dominate a constant. So we love constants. They're like the best thing we can hope for in algorithms. Any n to any power is going to dominate that. And you can even generalize this. This even works for fractional powers, actually. So this would show, for example, that that 1 is big O of the square root of n, or that the square root of n is little o of n. So an algorithm that takes square root of n time is going to be better than an algorithm that takes n time. Okay. But what's a little trickier to show is with these exponentials. So here I have to recall something from Math 111, which is L'Hopital's rule. So I'm going to use this theorem still. So I'm trying to make this look nice. So I still want to, I'm going to look at this limit as n goes to infinity, but let me look at a different example. So that's a little harder than if things are just polynomials. So if I have f of n, we'll start off maybe a little simpler and just say f of n is n. We'll do n squared, okay. And g of n is 2 to the n. Somehow we want to prove that, I mean, when I looked at this plot, I saw that the 2 to the n crushed n squared eventually. So this brown curve is going to be above the orange curve. But how do I prove that? So I'm going to prove that f of n is little o is little o of g of n. Okay. Well, let's just try to apply this theorem. So what I have to show, or one strategy for proving this, need to show that the limit as n goes to infinity of the ratio of n squared to 2 to the n is 0. So this is what we have to show somehow. So what we can say is, now we recall L'Hopital's rule. From calculus, which says that if, so one of the, it says a few things, but one of the things that it says is if the limit as n goes to infinity of f of n is infinity, so if f of n just grows and grows and grows, which all of these do, except for the constant, and the limit as n approaches infinity of g of n goes to infinity. So these both do. So n squared and 2 to the n grow infinitely as n gets larger. They'll get bigger and bigger and bigger and bigger. So if they both get bigger, it's not really clear like what's infinity over infinity, right? And that's the problem when we evaluate these limits. So n goes to infinity and n squared goes to infinity. So I had to do a trick to actually show that the ratio of the two infinities ends up going to 0. Infinity over infinity, okay, very strange. But there's a rule called L'Hopital's rule that says if both of them go to infinity, and the limit exists, so that either it turns out to be a constant or 0. Then it's true that that actually the limit equals the limit of the ratio here. Sorry, I'm trying to get my formatting right. This is the downside of not having a blackboard to write on. But my handwriting sucks, so it's probably fine. Anyway, what we could say is the limit of the ratio is actually equal to the limit of the derivatives, the ratio of the derivatives of two functions. So now here's where we have to think back to derivatives a little bit. Okay, so this is what L'Hopital's rule says. Okay. All right, so let's try to take the derivatives of f and g. Okay, so that's not too bad because we just remember the power rule, right? So the derivative of f with respect to n is 2n. Okay, that's not too bad. What about the derivative of g? So the derivative of 2 raised to the n. Well, I'm not going to prove this now, but that ends up being the natural log of 2 times 2 to the n. Okay. So now what we're going to try to show is that actually the limit as n approaches infinity of, instead of n squared over 2 to the n, we're actually going to try to show that the limit as n approaches infinity of 2n over natural log of 2 times 2 to the n. So natural log is log base e, for those of you who don't remember. So this is really what we're going to try to show now, if we go back to our example. So where f of n was n squared and g of n is 2 to the n. Okay. So here's the facts. The derivative of f of n is 2n. The derivative of g of n is natural log of 2 times 2 to the n. Okay, now I'm not done, because these are both still going to infinity, the numerator and the denominator. So I'm still going to have an infinity over infinity. So I need to go one more time and take another derivative, actually. So then the second derivative of, well, okay, so that's going to be the derivative of 2n, which is just the constant 2. And then the second derivative of this, it's going to be another factor of natural log of 2. So natural log of 2 squared times 2 to the n. So these are, I'm just applying rules of derivatives here. And you might want to go back and review some of these, but we're only going to really need it here. So just kind of bear with me on this. Okay, so anyway, now we're able to write this, we're able to say that, okay, so if the limit exists, then we can evaluate it as now 2 over natural log of 2 squared as n goes to infinity. Well, now this is much easier to see than what we started with. So we started with the limit as n goes to infinity of where did I write that? We started with the limit as n goes to infinity of n squared over 2 to the n. But we applied L'Hopital's rule twice, and we got it down to showing, well, that's equal to the limit of 2, a constant number, over this, which grows as n goes to infinity. So this ends up being 2 over infinity, which is 0. All right, so we just proved, so this proves that n squared is little o of 2 to the n. And actually, more generally, you can use the same proof technique to show that for any n to any power a, so that any n to the a is little o of any b raised to the n. So here I showed that n squared is little o of 2 to the n, but it's also true that n to the 1/1,000,000th is going to be dominated by 2 to the n, which is interesting. N to the 1,000,000 seems like it's grow really fast. But what we managed to prove actually is that any exponential, is called an exponential, any exponential will eventually dominate any monomial. So that's interesting. It's a little harder to prove. I'm not going to prove now that actually the factorial dominates all of them. But this is the rigorous framework for showing this. So now I just want to do a quick exercise on Canvas on little o. So making sure that you understand the hierarchies. Okay.